Good morning, good afternoon, everyone. Before we begin, can you send me a chat if you can see my slides and you can hear me? Thank you very much, guys. Ethan, Shufang, Mateusz, Rita, thank you very much. Looks like we are all to go. On behalf of Web Edge Solutions, I would like to welcome you to our today's webinar, Data Science Using Python. A similar webinar I delivered about 9 months ago, back in March. There are some additions, some changes, but for the most part, it's the same talk. Probably there would be some other questions and other angles. So for those of you who had attended me like back in March, just feel free to drop off. But if you have, I don't know, some time, it would be probably worth your while. I'll try to make it interesting. So my name is Mikhail. I'm the Director of Curriculum Architecture. I will be your presenter today. A little bit about myself. I've been in IT for more than 20 years, going back to kind of golden days of simple, straightforward proprietary tools, and things have been changing. And about 5 years ago, my focus changed to using open source projects, particularly those in the space of big data and data analytics, data science, machine learning. So I understand you are here because you would like to know about the things data science or machine learning and how it possible to do with Python. Python has become probably one of the more popular language in this space. The other competing language is R, but Python gives you a little bit of a more standardized API for fitting models, for doing predictions. In case of R, it's a little bit less organized because it's written by statisticians, and they developed it in a way that essentially people contribute those thousands of excellent top quality packages, but there is no kind of a homogeneity. There is no standard API, and sometimes you're kind of scratching your surface trying to understand how to kind of make use of the models. And the examples are sometimes cryptic, and description might not be quite transparent because, as I said, it was created by statisticians back in, it was New Zealanders, a couple of guys who started that, and eventually R has grown to become really powerful tool. But we are talking about Python because Python can be found across systems. You can find Python on Hadoop, Python with scikit-learn, TensorFlow by Google. Python is just omnipresent language. In itself, Python gives you all the tools, and at the same time it gives you the flexibility and transparency of the language, which essentially programs, if you understand the idioms of Python, they read as plain English. Okay, enough for that kind of intro to kind of why Python, but let's take a look at why data science, machine learning, and AI. All those things are just getting so much traction that people in various verticals have realized that machine learning, data science have come out of age, and they have become mainstream. A little bit of confusion as to what is what, how would we distinguish? So data science is a bigger thing. It's kind of an all-embracing label, which includes machine learning as an activity with algorithms and its specific discipline. Which is part of machine learning. And artificial intelligence, it's more of a set of procedures, activities, algorithms to substitute or emulate, augment, virtualize human activities like driverless cars. It's more about artificial intelligence rather than machine learning, even though machine learning makes it possible for artificial intelligence to do what it's supposed to do. So this is the traditional kind of presentation for those people who are new, and I don't expect everyone understands everything about data science, and this is one of the slides that you have to, I guess, see it at least once. And those people who have seen it on many occasions, so bear with me, you can take your eyes off the screen. So as you see, data science is just a conglomerate of activities. So data science in this Venn diagram sits right at the core. That's the centerpiece, and around it you have all those fields, problem domains that make data science what it is. So on the right-hand side, the upper right, that green circle includes math statistics, all that kind of very rigorous knowledge of how to use math statistics and similar disciplines to acquire knowledge. Hacking skills, it's just a very, I would say, loose term to describe what people do with programming languages, software packages to translate formulas, algorithms into algorithms and make them work on computers. Expertise knowledge at the bottom, it's kind of a really is a pillar to support everything. Business drives our needs, whether you're in marketing, whether you are in other fields, in banking, financial, maybe engineering. Everything is the cornerstone of your business is actually the business. All other activities, they essentially depend, and they are about to satisfy the needs. Whether you're Google, a big company or small company, what's your business? What's your business model? And then everything is just as a natural follows naturally. So we've got some intersections. I'm not going to spend much time, but essentially machine learning is about, it lies at the crossroads of software development and math. The standard pipeline, so machine learning data science, it's not about working in isolation with algorithms and models and just thinking about yourself as someone who is isolated from the rest of the world in that laboratory where you have everything pristine, clean, and white couch. That's what you're wearing. In fact, it's the whole thing. It's a set of activities, and you need to understand it, because starting from the left, data integration or acquiring data, cleaning data, sampling, modeling, going all the way to the right, it's what constitutes it. And you will become quite efficient if you understand how your data actually ended being in your data science lab or any other environments that you use for your experiments. So once you understand this, you definitely increase your chances for successful and valid models that you would create. And by the way, Python supports all those things. So you can acquire data from any data sources. You can connect to a relational database. You can scrape data from the web. You can get data in raw format from Hadoop. By the way, Apache Spark is one of the popular systems to do machine learning on Hadoop. Mostly that's where Spark is being used. And one of the languages supported in addition to Scala, Java, and not RR is only for standalone, and Python is one of the languages. So you will have transferable skills if you kind of start working with Python on a standalone kind of type of application, single-threaded, using your laptop or desktop, and you can always project or transfer those skills into a clustered environment like what Hadoop gives you. Okay, and that's pretty much by way of introducing why Hadoop, why Python actually gives you that overall access to every block, every piece of this analytics pipeline. So Python in itself, it's just really a toy language. It has some very nice idioms. It's well designed, no brackets. Sometimes when people get started with Python, they get frustrated with that tab kind of indentation, and people just not comfortable, not using curly brackets, and the fact that the language is loosely typed. It's not Java, it's not C#. Everything is just like JavaScript. It's dynamically typed, and that's a strength, and at the same time, it's its weakness. But I guess its strengths outweighs weaknesses, and Python has, in true sense, become the kind of the power engine for moving data science, machine learning algorithms ahead. So as I said, Python is great kind of a shell, if you will. It's interpreted language running on a single thread, the usual kind of stuff. But in order to make it really efficient, because efficiency is one of the critical factors of any machine learning or data science tool, is to use efficient libraries which have interface to native capabilities. SciPy was the response to the weaknesses of Python in the field of handling lists and data. Everything was an object. Object has meta information, lots of runtime data around it, and it's not really efficient. So you are better off to use primitives. And through NumPy library, SciPy achieves that efficiency. Essentially, it's a C written kind of a native code interface where you take a list of Python non-efficient structure and translate it into, map it into the local structures used by C, so where you can get access using point arithmetic, which is very efficient. Okay, SciPy has lots of good stuff in it itself. It deserves all the kind of kudos. It supports linear algebra. It supports, I guess, there'll be some coverage of what SciPy does. Pandas gives you a data frame, a way to handle tabulate data. Scikit-learn, that's where machine learning is all about. That's where it's happening. It uses NumPy, in some cases Pandas. Essentially, it just it builds on top of the existing investment done by SciPy. As I guess Isaac Newton said, I can see further because I'm standing on the shoulders of giants. And Matplotlib is the graphics package, which is absolutely indispensable. SciPy, I started talking about this, but let me just quickly go through its ecosystem of open source software for mathematics, science, engineering. It's a fantastic tool written in Python, but where it's needed, it can go through NumPy to the native interface. So linear algebra, there would be an example how to use NumPy for KNN. Single processing, which is important for engineering and for fast Fourier transformation. Okay, so NumPy, as I said, gives you that robustness and performance that you cannot achieve with the existing Python's lists, Python's arrays. It's open source, and at its core, it allows you to create an n-dimensional array. So it starts with like single array, but you can reshape it to make a matrix, multi-dimensional matrix, like ND array, n-dimensional array. And that structure sits kind of beneath Python runtime. A couple of select operations to show what actually you can achieve. All the operations are vectorized. By the way, the same thing happens with R. That's what makes R and Python very appealing to statisticians. Essentially, you treat an observation variable as just an array, and you apply a particular transformation to the whole thing. In more prescriptive imperative languages like Java, you'll have to do it yourself, unless you start using lambda operations for map, reduce, and filter. Okay, Java is catching up, but it's not natural for Java developers to use that mentality. So you see, we've got an array. NP is just a reference; it's alias for imported NumPy package, and we take the list of Python and we convert it into the native ND array, and we can multiply that pi with every element. So the output would be essentially we do a cosine function. You see, just trigonometry is just part of it, and we've got the output, which essentially gives us the points representing on the cosine line those points on the right. So filtering is as easy as just using a predicate. You plug the predicate, and that source array would be selected, and all the elements that are even would be selected. So that's the modulo operation, quite descriptive. By the way, I didn't mention this. If you have any questions, just let me know. Plug it in into that Zoom webinar if you would like to ask something. I'm not going to unmute because we've got quite a large audience. I don't want to upset other people with background noises. Again, use the chat window, plug in your question, and we will have a Q&A at the end of this presentation. The presentation is scheduled to run about 45 minutes or so, so there'll be some time for your questions. Okay, hopefully I'm not going too fast, but I just want probably to make more time for your questions, and I want to manage your expectations. I probably won't be able to answer some of the tricky questions, and but at the same time, I'll do my best to at least give you some direction, some clues. Reshaping is very important. So reshaping is changing away the dimensions of your structure. So we've got a standard list. By the way, the biggest difference between Python and R's structures is that R uses one-based indexing. Python follows that traditional zero-based indexing, which sometimes gets in the way, particularly when it comes to errors like odd by one looping, but Python compensates it for using idioms. But still, it's not natural for people. And people like at Microsoft, when they created that Visual Basic, essentially they adopted the same approach, which just I guess attests to its runaway success. So what we do here, we just reshape, of course, 4 rows by 2 columns, 8 elements should be reflective of the actual 8-element structure. Okay, and then you can apply some matrix-based linear algebra operations. Okay, let's demonstrate the capabilities of NumPy when it comes to machine learning. Some of you might be familiar with the KNN algorithm. It's called the K nearest neighbors. Essentially, it's just a way to perform classification of a particular dot. So you have your data, which is called like training data. Although in this case, there is no training phase because it's just direct shot. And you have the data that you already know how it's labeled, good, bad, or maybe stop, go, maybe multidimensional like stop or like hold, buy, sell type of logical operations. And those operations would be mapped to categories. And in order to classify a particular new dot, or maybe an email coming in and you have a spam filter, that's a good example, like whether how you would classify this email being a spam or belonging a non-spam. So spam should be treated harshly, kind of relegated to I don't know, to kind of a spam bucket. And let's take an example how you can use just plain vanilla NumPy to do this KNN, that kind of a classification. Currently, there is no labels, but you'll get the logic. So we've got a matrix which consists of so many rows with 3 columns, right? And we would like to classify, or actually find the closest points. It's up to us how we want to do this. Just 1 closest point, 2 closest points. Usually it's an odd number, like 3, maybe 5, and that odd number allows you to set a vote because all the nearest neighbors would essentially vote for this guy, saying this guy belongs to us, and there should be some break. And we've got the point which essentially scaled the same way as the rest of the points. And we're using the Euclidean distance, like dot between distance between P and Q, or Q and P. It's a reversed relation. It's expressed as follows. So we find that square root of squares, where we find differences between the corresponding attributes or properties of Q and P. In our case, it would be like 4, 5, and 3 minus all the dimensions, all the values of the vectors from the source P matrix. Okay, and Euclidean distance, by the way, is a critical piece. It's kind of a second norm whenever we want to find the proximity or find the distance. It's just one of the standard way that mathematicians, statisticians use to find proximity of objects. And then we apply that idiom of Python, enumerate norm. Norm is essentially difference. So this guy would do all the heavy lifting. Essentially, it would create a list of differences between the P matrix and the Q, going element-wise. P and minus Q, it's a vectorized operation. As I said, we do axis equals 1 across all columns, but essentially this is an idiom saying that I would like to do it for all rows. And you have just one value. It would be a list that you can enumerate. Enumeration is it's a way to extract both indices and the value. So you can create the key value items right away. So curly brackets, it's just a way to create a dictionary. So that dictionary essentially would contain the key value pairs, where value would be the difference between the points, and k would be a range in the range of 0 to the number of rows. We perform sorting of all the dictionary items, where key would be lambda. It's essentially inner function, where we take value. We can take actually the key if it's 0. I'm not going to spend much time on describing what Python gives you, but as you see, it's quite efficient. It's very compact, and it's very fast because it uses internally the structures which are very efficient in terms. And when we do the sorting, we get those lists where it's a tuple with the indices into the array. 2, 1, 6, essentially the top, the closest one, the closest neighbor would be the value element at index 2, like 0, 1, 2. So this point, and you can compare it visually, 3, 4, 4, 4, 5, 3. So it looks like the machine has identified that those 2 points are the closest to each other in that Euclidean space. It's a 2-dimensional space, 3-dimensional space. Okay, so that's what happens. Second closest would be the one belonging, it's the second element, right? It's a 0-based 7th element. And in this way, if you know the labels, known labels of these guys, you essentially can say, I can classify Q as belonging to the to that crowd, which essentially is represented by those 3 points. Okay, so, and you did it just using KNN. You don't need machine learning. You don't need anything else. It's SciPy, actually NumPy, and that gives you all the benefits. If you compare that algorithm with the traditional way of using machine learning, scikit-learn is the package that gives you all the algorithms. I'm going to talk about this shortly, but generally it gives you all the power of using standard interface. I mentioned this, and let me just quickly highlight those points. Unfortunately, I cannot do it because it's PDF, and don't know why it just doesn't allow me to annotate. Okay, anyways. So let's move on. So fitting is just a way to fit your model, to train your model. Fit is kind of a train. We know we have the whole labels for trained. So currently we don't have any labels to classify it. Our training data set here, we provide the known, a priori known labels. And it doesn't show where we go data train data set, label train. Essentially, just think about as some sort of data sets that we can provide. And then we can use that model that has been trained. Actually, the training, there is no training happening here. We just take the data and we get the nearest objects. But at the same time, we have, with scikit-learn package, we've got some organization under the hood. So it does, it finds some wiring, and it kind of creates some structures which would be conducive to parsing when you do prediction. So we do fitting the model, we do the training, and then all supervised learning that KNN is part of, we can do prediction. So we get a data set coming like in the form of those queues. It can be one dot, can be multiple dots. It can be a representation of emails, presentation of maybe some vocabulary, some texts, tweets, whatever the case might be. And it would yield you the label, predicted labels. And now we've got two pieces. We've got label, actually it's not shown here, but when we do testing on the data, it would generate a label test. Actually, that's we're using data test for doing predictions, and the actual label tests that we are using for associated with the data test is, again, is not shown here, but it definitely needs to be present. So when we do this import of metrics comes with a confusion matrix, and that's what you essentially get at the end of the whole exercise. So that would be part of that. That's where you will try different models, and you will perform model validation, and you will see how accurate the model is. Whether you would like to discard the model, maybe you'll use some hyperparameters. And the point is, we build this confusion matrix. Confusion matrix lists this 2 by 2 in our situation. We've got just very simple structure. We've got 2 classes that we want to predict. And we've got 2 columns. Columns represent the predicted values, and rows represent the actual, the true labels. And as you see, we've got 699 good predictions, 159 false predictions, false positive, and for second class, we will have 400. We've got 3 neighbors, but we are using two classes here because we've got this table. Again, you have the whole stack of all the things. You can train the data, you can do prediction, and you can do confusion metrics to give you that assertion as to how accurate your model is. And you can find it, you just can do basic math to find what the accuracy is, about like 20% accuracy, which we might want to improve by playing around with that neighbors. We might want to increase it or maybe decrease it. Maybe we will add something during the fit. There are options for that. I will refer you to K-neighbors classifier page on scikit-learn. Okay, pandas is a very popular open source library. It provides high performance, memory efficient. All that stuff is good, but it's good for small data sets, not very large. When you start going into that kind of hundreds of thousands, if not millions of observations or rows, things slow down dramatically. Particularly if you don't use indexing and you're not kind of doing very efficient processing. In these cases, all the bets are off. You either have to switch to, say, Apache Spark to run on Hadoop, or maybe to use some subsets, a kind of a smart sampling, where your sample would be very representative of your overall population. Okay, it builds on top of NumPy, and it has great interface for data aggregation, you can do pivoting. There would be an example. In fact, it has 2 data structures, but the main one is data frame, which is similar to a relational database table or Excel. I believe a major influence was from the R data frame object. R had it as the primary structure alongside with vectors, lists, matrices, data frame. Python didn't have it. Python has at best the dictionary, and they eventually borrowed the same idea, and it's quite descriptive, and it does the job. Essentially, it's a matrix with some meta information in the form of column names and what is the index, and it has some other internal hooks that you can use to get descriptive statistics like mean, standard deviation of every column. Just nice API. Some people complain that it's not consistent, but I guess it was written by one guy, and he did a good job. You have interfaces with various data structures, CSV, Excel spreadsheets, and SQL databases. So pandas has lots of capabilities for data science. One of the things that people just miss is that you have to clean data. You need to do something so that down the road, the flow is from left to right. So that's the workflow that people are using. So to clean the data, to remove outliers, maybe if you have non-available data, to plug in something or remove data. It happens, as you see, very early in the game. You are here, and probably that's where your main focus would be, but you should be also aware of those activities. And usually, you would have what you ask for. Your maybe business-to-business partners would supply data which has lots of missing data. So for that, pandas gives you a very nice API for plugging in those missing data, repairing your data sets, essentially, plugging in the holes. So operations such as grouping, aggregation are very appealing. Pivoting as well. There would be a slide explaining what actually it is. So let's see how things work with pandas. Even though it's just pandas, but it gives you one of the activities that are absolutely indispensable in case of the data science projects wall-to-wall, if you're responsible for kind of an overall cycle. So you read a table, it can be just any flat structure, separator between columns is comma, header is none, meaning there is no captions, and you get a data frame. So the output of that PD, that read table is class method of PD that we aliased here, df. Now, since we haven't specified the names of the columns, we could have done it if we wanted to attach that meta information. The system would just supply the traditional zero-based indexing. So the first column would be 0, second would be 1, and so on and so forth. So if we've got some missing data in a particular column, let's say first column, we can do an interpolation. Interpolation supports a number of methods or strategies like linear. Not all of them widely used, but whoever worked on this was just probably carried away to do that. Linear and the first one and the nearest are the best ones. So essentially it takes into account the values in the nearest cell, actually depending on the position of your cell, and it will plug in that value. Essentially it just replicates the data from your closest record. In some cases you might want to use something more drastic, like just say, I would like to use something which would be just a single thing. You can do for reporting like, again, there is another method like fill not available, just put dash in place of say not a number value. A better still approach is to use something meaningful for numeric values. So for the second column, which probably has some integers, or maybe it has some doubles, we just find the mean value for the existing cells in the row and in the column, and we would replace all the not available data, missing data with that mean, which is probably a very drastic approach, but it might make sense. Because if your data doesn't have a big kind of scatter, a big range, your variance is not big, mean would be a very good representation. So in this case, you can salvage. Let's say you've got 10 columns, right? And in one column, you have this missing data. And in some cases, people take this approach, I'll just throw out that row altogether because it has some corrupt data. And you can salvage the whole row with kind of some probably potentially valuable information by just plugging in something which just makes sense. Mean is a descriptive statistics, and descriptive statistics, it's just part of the inherent part of the whole setup. Okay, so moving on, group aggregation and pivoting. So let's say we've got the input file that contains like 4 columns. Key performance indicator ABCDE, probably the letters of the English alphabet, value of that KPI, and scale, medium, small, large, and movement could be down or up. It can be anything else. It can be, let's say, performance of a particular index on a particular product, or maybe on a stock exchange. So we read this table as follows. We use pipe as a separator. And the system would recognize that we've got the captions, and those captions would be read and automatically mapped into the properties of the data frames that we just created. And now what we can do group by. So this statement reads as follows. We would like, actually, I'll read SQL. Maybe later on, it will be confusing. So we create this intermediate structure, which is essentially a product of grouping data by scale. We're grouping data by scale, like medium will be globbed together, small would be crowded together, and we do the search for the value for every group. So now that you've got this transient structure, you can apply min, max, count, sum. Nice. So if you would like to compare that functionality with SQL, here it goes. For example, if you want to do sum, which is the last statement here, we do sum of value for this type of thing. So given that our data frame is in fact stored in a relational database. And you can also do pivoting, like Excel folks, they love it. Pivot gives you a way to take some categorical or leveled variable. Column, like movement, you see movement has just two levels, down and up. Movement would be kind of blown up, and you will have 2 columns, which would be down and up, and it will perform that grouping, which is a very nice kind of operation that you might see. So we specify column movement, and the pivot would actually look up movement. It will find that there are down and up 2 values. It creates this pivot table on the fly. So for A performance indicator, we will see that it was 390 and the movement was down, nothing for up. That's why we see none. So when you generate this report, you can, I guess, customize it the way you want. But if you want to get rid of this none, use this fill NA, so that instead of none, there would be a dash. Okay, and this is ready to use report. So higher ups, like executive summary folks, they will see that as a very nice representation of your potentially large data set. Okay, it shows you can do grouping, you can do pivoting, just explore this capability. So now scikit-learn is the primary language, primary package for Python, which is built on top of NumPy, SciPy. It gives you a great deal of functionality. Currently, it's still sub 1 version 0.20 or something, but it's actually being used in production quite extensively. Some people don't like Python. They say, okay, I'm better off to use Java or using, I don't know, whatever systems they want to do. But Python gives you that developer agility. You can set up and tear down your models much faster. Your development cycle would be shorter compared to what you would have done like using that kind of a Google type approach. We will create this in C++, and that's kind of the rule. Absolutely good position because they have the name to stand for. But if you do your data science projects inside your company, probably you can start with Python using scikit-learn. If not, then probably you would need to look for something else. Okay, so, scikit-learn has that advantage that I mentioned quickly earlier, that it gives you that homogeneous, uniform API for machine learning. It can be text, it can be numeric values, whatever supervised and supervised learning you have. You will find in every algorithm the standard set of APIs. You fit your model, you train it, you're trying to let the machine learn from that thing. It tries to fit to learn and fit a particular model, formula, parameters into that formula. It has predict, transform interfaces. And sometimes you would see some other methods like scoring to give a metric how well your model performed. Some methods don't have it because, like unsupervised learning, like k-means, for example, how can you measure the accuracy? That was a question recently, and it's it's just not applicable at all. In case of R, if you would like to contrast with R doesn't have this uniformity, and that sometimes gets frustrated. And by the way, same quality, same output. If you set it up correctly in R and Python, you can compare apples and apples. Documentation in scikit-learn on the scikit-learn website is excellent. So people ask a question, so how should I start? Just go to the documentation page, and whenever you come across something that you don't understand, then probably find something on the net. Okay, data splitting, and it's important for you to use your data for predicting, right? But how can you predict? First, you need to train your model. And let's say you've got just one data set, and that's all you got. How can you use the same thing to do the training and then to prediction, to use it, something that your model has not seen yet? And for that, you need to break up or split your single data set into two parts. One would be used for training. Usually it makes up 70% of the initial data, and 30% the rest for using training. There are some other techniques. I'm not going to go much into this, but the point is that scikit-learn gives you tools and algorithms, packages for doing exactly this. That's the beauty. It's kind of all-embracing. It has support for every area of activity, whether you just ingest data, where you would like to maybe scale your data, split your data, and run some models. So I guess that's the last slide that I would like to go through, is just to show how you would use scikit-learn for k-means. This is unsupervised learning. You would like to predict centroids, points of convergence for certain parts of your system. And the API importing and everything is absolutely homogeneous. So you read the data. We're using a data frame now. And what we do, we import k-means from scikit-learn. Cluster is that unsupervised clustering algorithm repository. K-means we specify. That's the only thing that we need to do. How many clusters, how many groups of similar, semantically cohesive dots in that space we have. Random state is a way to set the random seed so that you can have the same model reproducing the same result over and over again. One of the common mistakes for people to start using all those algorithms is just not to set this random state, that random seed. And because of that, lots of randomness that happens under the hood would shows itself that the results might fluctuate. They might not be exactly the same, and it would be very frustrating that in some cases, if you have a corner case, like a local minima or something, you would like to demonstrate to your friends, and God forbid, to higher up, and you show something which you essentially cannot reproduce. It shows totally opposite thing of what you wanted to get across, right? It happens, and for that, don't forget setting the random state. We do the fit. Again, fit is a standard. The standard API. We take a data frame, which is pandas data frame, and we build a model. And that k-means model now can actually produce, you might kind of argue, so why we have this underscore? It's kind of a little bit of a Python-y thing. they love it. Other languages, users of other languages, they deprecate, kind of look at this with kind of a frown, saying, okay, where's the camel notation? Why so many underscores? But I guess you'll get used to it. And we've got 3 clusters, and we've got two variables, two properties, or 2 features, and those would be the centroids. Okay, X and Y for the centers. Now, when we have this model, we essentially can predict the output. So we can send a matrix of just a list of points that we would like to predict, and the system would give us those indices. And indices would be, this would be the 0, second row would be 1 and 2. So those would be the IDs. If we have more centers, like 4, more variables, if you have more clusters, we would have more rows. If we have more features that we would like to predict, there would be more columns. But in fact, that system essentially contains everything that you might need to perform a very intelligent grouping. And your involvement is limited to just specifying the number of clusters. And that's it. You get the data, you let the machine learn from the data, it will spit out that list of, that matrix of centroids, and voila, you can predict the values. And by the way, you can serialize k-means model to save it so that you can get it back probably on Monday after your end of your Friday's experimentations, and you can continue, which is just a great tool. And for k-means, you can use now k-means to do actually very fast prediction, because prediction happens by just using some kind of a decision tree-like comparisons. There would be some boundaries established. System would serialize it in the form of kind of that heuristic. And whenever, so fitting learning the model, let it train on the data, would be a very time-consuming phase. When it finds that those centroids, it might be quite a long process, depending on the amount of data that you have. But prediction is extremely fast. So essentially, you can use this model for very fast classification near real time, if not the actual real time. So that's one of the benefits of that system. Okay, so that's all, I guess, what I've got for you. We've got today applied data science with Python. Some of the material has been borrowed for this slide deck, not one-to-one, but some of those. Okay, so that would be the time for me to take any questions that you might have. So type in your question. A slide deck, I believe, Mehdi, I believe that you have received that invitation to that webinar. So the link should be there. I unfortunately, with that Zoom thing, I cannot really share my slides deck right away. If it were, I don't know, go to webinar from Cisco, I would have uploaded it, but unfortunately, sorry. I will follow up with our guys who have sent up. If you are on the distribution list, you have definitely, you should have received that slide deck. More questions? I see no questions.